the more traditional one where now I get more messages. This meeting is being live streamed. Okay, yeah. The more traditional way of AI is more on expert system logics and so on. And the more what we call the modern one is more on learning and data science oriented. And you could say that this discrete event systems is more related to the traditional one with more of logics and planning and so on. But I still will use the notions and the things around this discrete event system. And I hope you will realize after some time that this is still a lot about what is called both traditional and also a little bit of the modern AI. It's a small part of the modern AI called reinforcement learning, which I will come up with in the end. And Professor Ojia will also support with some machine learning aspects. Okay, by this I will start my presentation. So then the classical question is, can you see? Oh, now I get this problem again. Let's see if I can. Okay, so there I hope you can see my slide.
Yes, we can see your slides, please.
Great. So the course is Artificial Intelligence, Logic Planning and Learning for Controller Design. Okay, it's something in the switch here which does not work. So I think I have to go back to... It's something strange in Zoom.
Yes, please. Is there any problem that you're facing?
Okay. I think we have to.
Yeah, we can see.
Now it works better.
Yeah, yeah, we can see it.
Now, so the outline for the talk today. First, a practical thing. Should we have one quarter break somewhere in the middle, or?
Yes, you can. Whenever you think that this requires a little break, you can take a break and you can ask. We can request participants to ask questions. Yeah. And we also request participants to please put your questions on the chat box. We will collect, and whenever Professor gets time, he thinks that the answers should be given of those questions, we will be
okay, so maybe we can take some time for asking questions also when we come to the tutorials. Yeah. Okay, yes. So I think time is running, and it's definitely time to rush on here. And so what I will do first is that I will try to present this notion of discrete event systems and what I mean by that, and then some more modeling details, and then how we can design controllers for this type of logical systems. And after that, I will go deeper into some aspects of logics and set theory before we can go on then with more details of all these aspects in the lecture tomorrow. So what is a discrete event system? Well, I used to start with looking at the three words. And one aspect of it is, of course, what is a system? And a system to me typically has a couple of subsystems, and it's quite often a kind of hierarchical structure. Although nowadays it's also very popular to look at this in a more flat strategy. So you have distributed systems which then communicate with each other in any way. And you could say that internet is in some sense a system where all nodes can communicate with each other. But I think the hierarchical structure also often has as a meaning. And the problem is, what we try to attack is how to reduce the complexity of these large systems. Another aspect of a system is that I assume that it has inputs and it has outputs. And then we are asking, what kind of state do you have in the system? And the inputs could be disturbances, but of course also control signals that are trying to influence this system. And then you have sensors that gives you information from the system by outputs. Then about the word discrete. And okay, then it's easiest to describe that by taking the opposite, because in at least control courses, which is my background, then we are typically talking about the continuous state space. And then we talk about temperature, pressure, velocity for cars, etc. And then we describe them typically by continuous differential equations, or in discrete time. We could also, that's one aspect of discrete. But today, and this course is not so much about discrete time, it's more about discrete space. And then we come to the following. The values of these states, that could be, for instance, instead of talking about the velocity, we could talk about the number of parts in a buffer. It could be the number of resources in a system. And for instance, if a resource is active or if it's idle, there are two different discrete states representing this. And the states could be just naturally integer numbers representing these states, but it could also be symbols, like a system is in an idle state or is in active state or a running state, etc. To start up with a very simple example, I take a buffer where we can also introduce some typical modeling behavior of this type of systems. And going for equations here, we can say that, well, let's say that this X is the number of parts in the system at the moment. Then if you add an input u equal plus or minus 1, then you add or you remove one part of this buffer, and then you get an updated number of this buffer system. So for instance, if u is 1 and the current state is 2, then the next state t at tk plus is then 3. This is an equation-oriented model which is, you could say, correspondent to the continuous state space models. But there are also quite common graphical models. And it was also promised that we should talk somewhat about graph theory and search methods in such systems. And you could say that this is the most simple and basic model for a discrete event system or for a logical system. So here we have this buffer, and the initial state with this small arrow say that there is no element in the buffer. Then when the event A happens, meaning that a part arrives into this buffer, you get one element in the buffer. And then you can get one more part by the same event, meaning that when A happens, you add one more part, and then you have 2. Then you continue with 4 such events, but then it stopped. Then you cannot generate more A's. And that means that you have a limited capacity of this buffer. It can only take 4 elements, and then it stops. And then after that, you can go back and take away one element by the event B. Remember that in computer science, it's also quite common to, instead of call these events, you call them actions. And in this case, I would say that action is quite a natural name. And if you go for, say, Markov decision processes, reinforcement learning, etc., and also formal verification, it's quite common that the name action is used. But in the community where I started my career on this topic, we called it discrete event systems. And an event could then be that the light is on, and then you stop the light, and then or say that, okay, that you arrive to in a room, that is an event, and you assume that event is something happen immediately in zero time, which of course, if you arrive to a room, is not a zero time event. It takes some time for you to enter the room. But we talk a lot about abstractions and simplifications. And one simplification is exactly this, that you assume that the event happens in zero time. Okay, so this was about the automaton, and it's also called finite state machines, because we normally assume that the number of states, the number of circles here, that they are finite. But it could also be called finite state machines or just state machines, and there are a couple of other names also, but we stay with that. Then there is another very famous and alternative way of describing this type of systems. And in some scientific areas and also more practical areas, these Petri nets are extremely popular. So they are actually more popular than the automata. And you see that one reason for that is that you get a bit more of a compact structure, because in this case, we have only two circles here, or two nodes representing the system. And then instead, the states are represented by these tokens. So this place, as it is called, the number of tokens in this state represents the number of parts you have in the buffer. So when an event A happens, one token is moved from this place, you could say the number of empty places, to the place where you represent the number of occupied places in the buffer. So then when one more A happens, the second token is moved, and then you have two tokens here and only two tokens in this free places, you could say. And then you can have events B, meaning that you take tokens away. And B requires, of course, that there is a token in this place to make B possible. And that means, of course, that you must in the automaton be at least in this, that, oh, sorry, or one of these states to be able to make a B. In this place, you cannot, or state you cannot take a B event, only the A events. At the same time as in this state, you cannot take an A event. And that corresponds to the situation where all the tokens are up here in this occupied place. So these models, they represent exactly the same thing. Now, a third way to describe this, which is actually a little bit of what I told you earlier here, but I formulate it now a little bit different. Actually more in, let's say, a little bit more of a structured way here. So in this case now, for this specific buffer, I assume that I have a discrete state space, which includes these 5 integers, 0 to 4. That is the possible values of the variable x, which belongs to this discrete state space. Now, the update, the change of this variable x is that the next value is x plus 1 or x minus 1. But this can only happen when the event A is executed or it occurs. And another condition, that x must be less than 4. It must be possible to add one more element into the buffer. And the opposite, you can remove one part from the buffer. If there is at least one element, if x is larger than 0, then you can add remove one element by the event B. So these two equations with these conditions describe exactly the same as these graphical models. Now we can also formulate this as a predicate. And I will talk more about predicate later, but I guess you are maybe familiar with this type of expressions. And then we can say that, okay, either this condition should be true, namely that the next value is equal to the current plus 1, and x is less than 4, and the event E is equal A. If that is the case, then this will be true, and you get this updated. Or this is exclusive, or actually, because E can only be A, B, or we could also add nothing, say epsilon, the empty event. But if this is true, it means that you remove one event, remove one part from the system. So either that or one of these two could happen. And this is not very readable, especially when you come to larger systems. But at the same time, you could say that it's perfect for a computational algorithm. I mean, this is just a graphical picture. So you need to boil this down to some mathematics to make a computer program out of this, and the same for the Petri net. And this way is one actually very powerful way to do this. Of course, this model where you work with more state space equations is also another way to do it. But to really formulate efficient models or efficient algorithms, I strongly recommend this way. And there are, for instance, algorithms like binary decision diagrams and another tool called satisfiability solvers, SAT. And both these are very well suited to represent and to make computation on this type of systems. We will come back to that later. So now I introduce another aspect, which we'll also talk a little bit more about later, namely that we could have a continuous system in the background, and then we try to make a discrete abstraction of that. And then my application now will be a simple thermostat, which is the classical application of what we call hybrid systems. But in the course, I just say that, well, this is just a way to describe also a discrete event system. So when the temperature is less than T0, the logical value y is 0. And then with this event y up happens, which means that you just cross this level T0. You get the logical value 1 saying that now the temperature is high, and then it goes low and high. And actually for this, you can also represent this as an automaton. So this represents that the temperature is below T0, and you have the logical value y equals 0. and here y equal 1. And you could say that this could represent the false value and the true value, if you like. And when you go from say off to on, or from false to true, that happens when the event y up happen, and that means that you get high temperature. So this is an extremely simple model for this continuous temperature signal. Well, just to make a short summary about discrete event systems, and actually these figures and most of what I've described so far, you have some lecture notes, and the first 40 pages on that is about what I will talk about today, the first part of this lecture. And that is actually what I hope in the end will be also a textbook on this. So this is a summary of what a discrete event system is. Okay, it consists of a set of discrete states where you have transitions between the different states, and you have also associated instances of events which, so to say, generate the dynamic system behavior. So typical examples of discrete events are mode changes, start an operation, send or receive message, discrete signal changes, and state jumps. Now comes a very interesting aspect here. Although a discrete event system normally is a quite small systems in themselves. You know, what I've showed you is very small systems. But what happens when you combine all these systems? Then you get what we called the state space explosion. Because just think about that you have a two-state model combined with another two-state model. Then you suddenly get 2 multiplied by 2, you get 4 states. And if you have 10 such models, two-state models, you get 2 to the power of 10. That is around 1,000 states. And now, of course, most small models don't only include 2 states. They could be 10 states. It could be a small computer program which is represented like a software, which could have, say, 10 to 100 states or something. And that means that you typically could get millions or billions or even more a number of states. And then, of course, the question is, what can we do when we have such many states, more states that we can represent in a computer, for instance? And that is, so to say, a big part of the challenge we are working with in my group and also in many other computer science groups in the world. And you could say that the last 30 years has been a big challenge on how to handle this type of complexity. And I will give you at least some flavors around that later also. And there is a very interesting abstraction technique, which means that you can reduce the representation of systems. So you could start with, I will give you an example later. You can start with this type of buffer systems, and from the beginning you have, say, millions of states. But the interesting property of that system could, in the end, be boiled down to only 2 or 3 states. And that small model still says exactly what kind of properties you have in the system, namely that you could have good behavior, but also some bad behavior. For instance, that you could reach a deadlock from which nothing more can happen. And here I used to give a small story for my students, and I will also mention that to you. And that is that I used to start with asking a locking alarm system for a car. How many states do you think there is in such a system? Is it even any one of you who would like to give a guess on how many states you believe that there are in the locking alarm system? Does anyone want to say something or make a guess?
2.
Okay.
Bipin, you were telling something?
Yes, 2 states.
2 states, okay, because you are thinking about the on-off, locked or unlocked, yes. But at least, you know, for a car, you have individual lockers for the 4 doors. So at least we must have, or say, about 10 states or something. Yeah, okay, I will not push you anymore on this. But when I had the students in the lecture hall, it's easier to communicate, and then people start to guess, and then some say, yeah, maybe there is something more in this. Maybe there is even a small software somewhere, and then they start, yeah, maybe it's 1,000 states or so, and then I say, well, much more. Actually, for BMW locking alarm system, we have got the software or a model for that, you could say, which represents that. And it's about 1 billion states, 10 to the power of 9 states in that kind of system. And let's say about 10 years or a bit more, when we started to analyze that system, it was quite hard. But nowadays we are able to quite quickly analyze that system. And it was actually possible to show that there was, in the BMW software, there was a small bug. So, and it's even a story, I think it has some truth at least, that it was a royalty from Thailand that was locked into his BMW car. So they had to crash the window or something to get him out. If it's true, 100% true, I cannot confirm, but it's at least a nice story. And we know that BMW had some problems with their locking alarm system quite a number of years ago. So what I will show in this course is that, okay, first you can identify that there is maybe a deadlock state where nothing more will happen. Or let's say, if you think about a computer, there you typically have the live locks, you know, this small circle moving around and nothing happens in the computer. And what do you need to do then? Well, you have to restart the computer. And of course, that is a very unsatisfactory situation. And think about if that should happen, if you are looking at the safety system of a car and autonomous driving or any type of control software related to satellites and so on. Of course, it's extremely bad if you have that kind of situation. And I will soon come back with a similar example where actually things have happened which have not always been so nice. Well, to verify, to find that error is one thing, but what I will also learn you in this course is that we can even repair that failure. We can make, so to say, a change of the controller automatically, which remove those bad behavior. And you could say that that kind of strategy is quite close to what also is considered as planning. Then you design a supervisor or a controller which only gives you the good behavior of the system. So then a little bit more about modeling. Going back to this temperature control, we could make it a little bit more advanced, and we could have an hysteresis here, which means that we have two sensor levels, T0 and T1. And in this case, we first need two logicals, one for the lower level and one for the higher level. And Y0 is for the lower and Y1 for the higher. And then we also introduce a control signal here. And then this is the thermostat strategy. When you get to the higher temperature level, then you switch off your heat. And then when you get to you pass the lower temperature level, then you put on the heat again. So this is typically how a thermostat works. So that can be now represented by first the 3 states for the temperature. 0, 0 means the lower level, 1, 0 means the middle, and 1, 1 represents the high temperature level. And you have the corresponding events here. If you combine this with the control signal, you can be either up or down, or 1 or 0. If you just combine them as they are, you get these 6 states and a lot of transitions. It means that the control signal has no restrictions. It can go up and down in any state. But of course, that's not a good behavior. We want it only to go up or to put on when you are in the low state, in this state. So when you have got the event Y0 low, then you are in this state. Then it's time to put heat on. And then when you have reached the high temperature, then you switch off the controller. So you could say that this is a specification of the desired behavior. And at the same time, it's a restriction of the original model, where you could say that you can skip some states and quite a number of transitions. And this is then also not only a specification, it's actually a model of the controller. Now you can reduce this further and say that, okay, now I only introduce events for the sensor signals, and then I have states representing the control signal when it's on or off. And when the temperature goes to the high level, then you switch off the heat. And when it goes below the low level, you switch on. Okay, this was quite a simple example, but it illustrates at the same time that you have model of the plant, you introduce a control signal, and you combine them together. And this is what we also will call the synchronous composition of these systems. That will be defined in more detail later. And then you get, in this case, a pure discrete event model. And in this case, you could say it's a little bit of a more logics introduced in this. And that means that in the specific states here, you have a specific value of a variable, namely u, a control signal. Now, the interesting thing is that this was a temperature control. If you look at the level of a tank, it could also have these 2 levels, H1 and H0, and the input flow to this via the input valve here. It could be just either open or closed. So this is a simplification where you only have a binary valve. And then the strategy is that you introduce, you stop the input flow when you pass this higher level, and you put on the input flow when you reach below the level H0. And this is also quite a simple, not that uncommon tank level control procedure. Here, actually, the same type of models will be used. And here is another very typical automation application, a cylinder with a piston rod, and it can go out when U is high, and when U is low, it goes to the 0 level or in. So this is the 0 level of the piston rod. And this could be a pusher. So when you say U is equal 1, then the cylinder or the piston rod goes out and push, say, a part away, and you have this type of cylinders in many automation solutions where you want to things to move around. Once again, a small summary. Generic discrete event models can be achieved, which can be used to describe completely different physical behaviors in different applications area. So here I showed you cylinder, tank, and temperature control, where you could say that in principle the same type of models are used in all these three applications. And models for control purposes can often be simplified, where a lot of details of the system behavior are not necessary to include in the design of the controller. And that was illustration of this fact, that here you have a more complex behavior, giving all details, all possible behavior. But for control purpose, we could boil this down to this simple two-state model. Maybe I should ask you if anyone has a question now. It's very silent, and I don't see anything in the chat. Okay, it does not look like that. Then we go on. So now we come to the question, how can we control this type of system? And well, then we assume that we have a plant and we have a controller. And by sending first sensor signals or sensor events from the plant to the controller, and then bringing back events to the plant, you get a closed loop system. If you compare this with, I don't know how much you have taken courses in feedback control, but this is actually a feedback control system where in a basic feedback control course, you have signals here. It could be that you measure the temperature, or you measure, for instance, the speed. And if the speed is too low, you had to say to the engine, to the motor, okay, increase the rotation in the motor to generate some more torque or force. But so in that case, it's continuous signals. Now we are talking about events instead of signals. But I have to admit that this is also an abstraction where in reality, when you control also this logical system, these discrete systems, the implementation is also most often based on signals. And in that case, it's binary signals. And it's a typical equipment called programmable logical controllers, PLCs. And you have a lot of them in factories, but also, for instance, I know that in say a bus where you control how to open and close the doors, there is also small PLC. A PLC is just an ordinary computer with some inbuilt interfaces to the outer world, to the environment. So in this case, you have logical output signals and logical input signals. But when you have these signals, it's also possible to abstract this to these discrete events. And that is exactly what I am doing in this presentation and in this way of, you could say that it's natural to develop theory and algorithm based on these events and actions. So when we then look at what is the model of the feedback system, well, it's typically a transfer function. Let's say that P is a transfer function for the plant and C is a transfer function for the controller. Here I use the Laplace transform, if you have seen that. Okay, if you're not familiar with that, you can just skip it. But for those who have seen this before, it could be interesting to see. This is typically a transfer function from the reference signal to the output signal of the plant. P plant multiplied by controller divided by 1 plus this same. So this is a transfer function for the closed loop system. So then, of course, a question, what is the model then of our system here? Well, here we introduce what I call a synchronization or synchronous composition operator between the plant and the controller. They should simply be synchronized together. It sounds quite intuitive. Let's see what that means. So now I have a simple model here, G1. In this case, it's just any model, any automaton, together with another model or another automaton, G2. But we could think about G1 as a plant P and G2 as a controller and see what happens. Well, now if we this double circle actually means that this is a goal state. You want to make an A and then C and come back to this again. While in the plant, we don't have any specific goal or marked state. You could stay anywhere. And then you could say that, well, this is more describing the desired behavior in terms of a specification or a controller. When you now synchronize these two systems together, what happens then? Actually, something strange, which I will try to illustrate here. What does this synchronization means? Well, then you have this will be defined in more detail later on, but I just illustrate this already now. You are both in the initial state 1, in this case, the first and the second model. Then the event A happens, and that is a shared event. And that must happen then in both to be able to execute that. So, but both G1 and G2 can go from state 1 to state 2. And in the synchronized system, you have this both state names, and this is also a marked state because it's marked at least in the second model here, the specification. Then you go via the event A to the second state, which is then 2, 2. Then you see here that you have some additional events, B, D, and C in what we can call now the plant model, but they are not in this, no, sorry, B and D. C is also shared, but B and D are local only in G1. And then they can happen independently of an interaction or synchronization with G2. So then assume that B happens. And actually, that is necessary to be able to execute the shared C event. But let's see first that from 2, 2, you go to 3, 2. That means that the first system is in the third state, and the second one is only in the second state. And then you are down here in the synchronized system. Okay, then you can make this shared C event because both are ready to do that. The first going from state 3 to 1, and the second going from state 2 to 1. And here you also see that in the shared system, 3, 2 via C to state 1, 1. Fine. Now you could say that you have a system behavior which we actually wanted, because we said that, okay, when you have made an A, you should then make C, not D. So this could be a desired specification. When you are down here, you shouldn't take the D way, you should take the C way instead. But now, formally, since D is a local event, it can happen spontaneously. It's not prohibited by G2. And what happens then? Well, the first model goes from 3 to 1. It means that you get 3 here and 1 there. And the second model is still in state 2 because the only thing the second model can do is to make a C event. But okay, due to the first D transaction in the first model, you have come to this 1,2 state. But after that, what can happen then? Nothing, because G1 can make an A, but G2 can only take C. It must first take C before it can make an A. So this is what we call then a deadlock state. And this is exactly the kind of bad behavior which we want to be sure that we can avoid. But okay, if you had only looked at this, say, okay, wasn't this a good model? Wasn't this an expected behavior? And you generate this system. And if this was a system where the closed loop between the plant and the controller includes billions of states, of course, it's totally impossible to find these deadlock states if you don't use efficient computer programs. There are actually good programs that are able to find these states. Not always. I mean, 1 billion states could be challenging sometimes, but we have developed algorithms where we are quite often able to handle that without any problems. In some cases, with some special structures, actually, we can handle 10 to the power of, say, 100 states or 200 states. I used to ask also, how many atoms are there expected to be in the universe? Does anyone know that? You can read on that in Wikipedia. It's about 10 to the power of 80 atoms estimated to exist globally in the world. Then we are able to handle much higher systems than that. But okay, how can we now correct this bad behavior? Well, the problem was that we missed something here. We missed to say that, well, G2 is still forbid D to happen. And that can be included saying that the set of events in the G2 model includes A and C, what you see here. But we also say that the set of elements, set of events, which we call sigma here, sigma 2, also include the D event. And that means that since D cannot happen in G2, it can also not happen in G1. And in that way, you get the good behavior. So this just illustrates the synchronous composition and the fact that we have to be a little bit detailed on the set of events in the two models to get the appropriate behavior. So this was about the synchronous composition. And remember that the model for the synchronous composition is this P synchronized C, the synchronization of the plant and the controller. And when you include the D event in the alphabet, you could consider G1 as the plant and G2 as the controller, and you get the quite nice closed loop behavior, because it says that you will get A, B, and then when you have this choice between D and C, well, the closed loop system will take a C. And that was exactly what we specified here. Okay, then the temperature example. Then we can say that the plant model was this unstructured behavior where the control signal can take any value up and down, any event up and down. And then you have a controller, which I specified in this way. It was exactly what I did down here. This was the controller I came up with for the temperature control. And here it is. And now if you synchronize that with the plant, you get actually this closed loop system. And what this says is that, well, we assume in that case that we start with the lower temperature. And okay, if you don't know exactly where you start, you could say that, okay, the initial state could be any place here, any state here, and then just waiting for the next event to see what happens. And in this case, we assume that when temperature goes up above the lower level, then you go to this state. And if you go up to the higher level, then it's time to close down the heat. Sorry. And then you expect that the temperature should go down first from the higher level and then to the lower level, and then it's time to put heat on again. And this is the model for the closed loop system. Before we take a break, I would, I see now that time has passed. Maybe we should, at least we can take a 5 minutes break, because we started quite late with the lecture. So at least a 5 minute break, we can say. Sure. So that means for my clock here is 11:37, so 11:42. Is that okay?
Sure.
Good.
Participants, if you have questions, please post on the chat box meanwhile.
Yeah. So, Aparajita, is this something? Have you? Do you think that most of the students have seen this kind of stuff before, or?
No, in fact, some of them are purely from computer science, and some of them are from control engineering. So those who are from control, maybe knowing better, maybe having some knowledge. Yeah. And those who are from computer science, for them it's a new something which is perhaps new. Although the finite state machine, they have probably they've read,
Yes, definitely. And my guess is actually, when you are a control engineer, quite many of the control engineers have not met this type of behavior, because it's at quite many universities this is not a part of the curriculum. It starts to come up now, but traditionally, I mean, when I was a student, no one talked about this. But for the computer scientists, you could say that, well, the control aspects is not very familiar. But as you say, I mean, finite state machines are very familiar, and but this synchronous composition, which is very crucial for us. Some people consider that, but there is a lot of dialects of different types of synchronization between these automata. So I think it's important to have that all in place. Okay, so I think I will take something to drink also. If there is something here, I will. So I think I stopped the video just for 2 minutes, because it's a lot of sound there for my water cooker.
Sure.
Oh, sorry.
Not audible.
So Sanjay, are you not attending? In fact, he just took a small break. So he was asking if it is 4:02, around 4:02, he'll be 4:12, he'll be coming back. Yeah. So participants, as a mandatory requirement, we are supposed to take a screenshot of all the attendees at the end of each session. So my request to you is to please put your videos on when we will be taking the shot. So Professor is back. Yes, please.
Yeah.
So there are a couple of questions in the chat box, Professor.
Okay. Yeah, that's nice. That's nice. Let's see. Let's take it.
So one question is by Sarvana Guru is that, is it possible to model human behavior?
Oh, yeah. Okay. That's, of course, a very interesting question. Well, there is one, I mean, human behavior, it's of course, it has so much possibilities. So then the question is it natural to model the human behavior by this type of models? And yeah, sometimes there are some applications. Actually, we submitted a paper to this case conference, which we heard about before, the IEEE Robotics and Automation Conference on specifically automation. And then when you introduce, say, reinforcement learning and take a discrete version of that, then how a human can act together with, say, a production system and together with a robot. So human-machine interaction, human-robot interaction. In that case, you could maybe say that, okay, when, for instance, it's critical that when the human is close to the robot, then the robot needs to move slowly. So you need to reduce the speed of the robot to avoid damages where the robot could hit the human. So security functions related to humans could be one example. Another thing I was thinking about, yeah, I mean, let's say that in the production unit, just of course it's a trivial example here, and I'm not sure if you think that is very interesting and challenging, but just to add pieces into a buffer. So this event A, when a part arrives into a buffer, that could be something generated to generate events. Could be made by humans. And here comes something very interesting, which actually took some time for me to realize that, because we are now talking about controllable events and uncontrollable events. And I will talk much more about that later in the course. And that is an example of when you push a button on a coffee machine or something. That's typically an uncontrollable event, but it's a human interaction with the system. So, okay, I'm sorry if you don't understand all my comments at the moment, but we will come back to that. And for sure, yes, human behavior or human interaction with a system can at least perfectly be modeled by this type of models and this type of behavior. Okay.
Next question. Sorry, you were saying something. I'm so sorry. So there is a next question on which Rajiv Das is writing very nice, which software for lab? Probably you'll be using MATLAB for?
Yeah, I was first thinking about how this transfer function can convert into digital system. Yes, and actually I will show you that later in my presentation today. Even now, you see that I will not. All the results will not be presented now, but we have also in the tutorial session, and I will give you examples if you have already seen examples now, and I will give you more of the logical part when we come to the tutorial session, and there comes also how you implement this. Yes, so it's possible. MATLAB, yes, you can actually. I'm implementing more or less all the algorithms which I present in the course here, I have implemented them in MATLAB because I'm used to MATLAB. Nowadays, it's also very common to use Python and so on. But yes, MATLAB and of course more powerful language like C++, etc. Are also possible. Okay, no audio video. Sir, I'm from mechanical engineering. It would be very helpful for me to follow if you cover the basics to automata theory while explaining the concepts and control with respect to formal language. Yes, that's something I will give tomorrow. Tomorrow I will present that. So yes, I mean, I introduced these circles and all these aspects of but by very simple examples. I hope you could at least understand a little bit of what I was talking about. But the more complete theory will be presented on that tomorrow. Yes, great. Thank you for the questions. Now I think we should go on.
Yes, please.
So let's share the screen again. So now an example from a robot system. And as you heard, I am quite active in the robots and automation IEEE Society on Robotics and Automation. And of course, especially the automation side, but I have had also leading a discussion more recently on how to improve the collaboration between robotics, which is the huge part of this society. You know, when you have these robotics conferences, there are like 3,000 attendances. And then, to be honest, automation is not, it's much more distributed in different areas. So there is automation in control, automation in other operation research areas, etc. And that means that automation within robotics is the smaller sister, so to say. And then to get a better collaboration between those, we have had interesting discussion more recently. And for myself, I started actually this type of work with quite much of relation to production and flexible production and the system of robots. So we say in automation that automation is not one robot, it's a set of robots, it's a system of robots. And then, of course, the interaction between the robots is central. So a very typical problem where we also introduce this notion of shared resources or a common zone in this case, I will illustrate here. So in this case, you see that two robots can work in the same area. Robot R2 can move around like this, and robot R1 can also move in the same area. And then simply the control or the coordination strategy here is that only one of the resources is allowed to be in this common zone. Then you can divide this common zone into a number of zones, and in that way get more flexibility between the two robots. So it means that if robot R1 is in the lower part of this zone, robot R2 can be still in the upper part of this zone. But that is more of details. Now I only assume that I have one shared zone, and then I just want to generate a control function which avoids that both of them are there at the same time. And this is this classical mutual exclusion problem, which you can see a lot about also in computer science literature. So what I do then is that I take a model for each of the robots. A robot can be either in an idle situation, it can be I make a request of this zone, and then I use this zone. And then when the C event happens, then I go back to the idle situation where I assume that the zone is not used. And why do I call it PI? Well, that's just because I consider this as a plant model. The plant model for the first and the second robot, I equal 1 and 2. Now, when you synchronize these two automata together, they both start in idle mode. And then let's say that the first robot makes an A1 event, then that is in a request, while the second automata is still in the idle mode. And then the first via the B1 event goes into the user mode, and the second model is still in the idle mode. But the second model can also go to the request mode by an A2 event, and then you get these different options here of possible states and transitions. And in the same way, as long as the first model has only make a request, the second model can also go in and use this zone. But of course, in this case, there is one forbidden state, namely that both of the robots are using the zone at the same time. So that's just an additional specification we add here, that this UU state is forbidden. And that means also that since that should be avoided, all the input transitions to that state are taken away. Because otherwise, the full synchronous composition also includes the B1 event and the B2 event from this UR state. But then just avoiding that state, it means that what you have here, what remains here, is actually both a desired specification of the behavior, but it also works fine as a controller. So the controller here just follows what the robots are doing. But if, for instance, the robots say, robot 2 say, I would like to make a B2 event, but then the controller say, no, that's not possible. You are forbidden to do that because it's not in my model. So that's the way how this works together, that the plant actually asks the supervisor or the controller, can I do this? Can I make this B2 event? And if that B2 event is not in the model of the controller, it's forbidden by the plant. And then you could say that the controller more works like a police, and that also means that it's more safety function, and we therefore also quite often call it a supervisor instead of a controller. Now I come to this space application where actually it's a similar behavior, but with some added feature. You can read on Wikipedia on this Mars Pathfinder, which it was a small equipment that was delivered by space shuttle to Mars, the planet Mars, and people had made a lot of investments and introduced software and control functions into this small vehicle moving around. Now, for some reason, it's hard to believe, but when they implemented this, it was a shared data bus. And then they said, okay, that there were two tasks, like you here had two robots, and now we have two tasks that should both use this data bus. But then they introduced a priority. One of the tasks has higher priority. But then they made a serious mistake here, because they introduced a specification saying that, well, the task with the lower priority, you can execute an event in that. But when the task with the higher priority had made a request, it means that you have gone from the idle to a request state for the task with high priority. Then you went to this state. But then the specification says that, okay, now the lower events, lower priority events, both A, L, B, L, and C, are not allowed anymore because they cannot be executed here. The only event that can be executed here is this CH event. So when the AH has been executed, okay, it can make a BH and then CH. And it's first when you have gone back to these states, also here, where the events with lower priority can be executed. So now if you add this specification to this model, what happens then? Then you get this behavior. When the task with the lower priority is actually using the data bus, and the higher priority has made a request, you are in this state. And when the high priority function has made a request, the lower priority task cannot do anything more because it was forbidden. As I said, when you have made an AH, you cannot take the lower priority events anymore, and you reach into this deadlock. And actually, this was what happened at on Mars. And what happened then? Well, what they decided as a procedure then, that okay, if something bad should happen, there was a timeout. If something goes wrong, say like your computer, if it should come into this live lock situation where it just circle around, nothing more happens, then you make a restart after say 5 minutes. And that was what they implemented, but for some stupid reason, they also forgot to save the data before they made the restart. So after this Mars expedition, they realized that they lost a lot of data due to this problem. That first they introduced a deadlock, which was in some sense hard to understand. And then they also missed the saving of data before they made the restart. Now I give a very bad description of what happened here. And you can read yourself about this on Wikipedia. For myself, I can say that this was something that one of our earlier PhD students recognized or found, and he tried to model the system based on the information he found on this expedition and this behavior. And you could say that, well, maybe it's only an academic example in the end. It was a serious problem for sure. They lost a lot of data. So we can say the millions of crowns was just burned up. And when we see this, we can just say, oh, how could they be so stupid? I would say that my explanation is that I think that they hadn't used this kind of thinking. They hadn't used this kind of models, try to describe what happened. And of course, we can always all make mistakes, but this was quite a costly one. So a short summary of the design of feedback controllers. The closed loop system is then modeled by the synchronous composition, where we can say that typically what the controller does is to restrict the behavior of the plant. And you could also say that there is typically a closed loop specification which expresses the design properties of the closed loop system. And there was also something here which I could emphasize more, that the specification typically includes both goal states or marked states, as we call it typically in this community, and also forbidden states. Then we have two typical problems. And the first one is what is the main task within computer science, I would say. And that is sometimes called model checking, but also formal verification. And that means that you have your plant model, you have your controller, you have a specification, and then you build a closed loop system, and you look at if the closed loop system satisfies the specification. So it's a verification, a test, but it's a complete test. All states are evaluated by this type of formal verification technique. And then you could get a question, yes or no. Is the system, does it fulfill the specification? Yes or no? If it does not fulfill the specification, if you, for instance, have deadlock states, etc., then you also get a way to find the bad states, a sequence of events that reach the bad state. And that's, of course, a good thing. And then it's up to the engineer to fix that bug in the software to avoid the problem. If we look at it from a controller synthesis perspective, then you could say what we do is that we take the plant and the specification, and then we compute a controller which satisfies the specification, which means that we sort of say automatically fix the bug. Now this sounds, of course, very nice, and hello, control scientists are much better than the computer scientists. Of course, that's not true. But this concept of synthesis is actually interesting. And after some time, we realized that there is a smaller community also in computer science which work more on temporal logic, which is a kind of extended logic, which I will come back to later. And they also try to represent and automatically synthesize automata or state machines for representing these temporal logic specifications. And there you could also say that there is a kind of synthesis included here. So there are communities both in computer science and in control theory that are able to synthesize these controllers. And actually, first when I gave this course for my students, I say, oh, the control scientists were first here, but it was actually not true, because there was some earlier initiatives on this reactive synthesis, which has a little bit different flavor, but if you interpret it in the right way, you can say that it's a type of synthesis that I have described here too. So now I come with some handwritten slides, and I'm sorry to tell you that quite much of what I will show you in the rest of the course will be of this type, because it's based on my Zoom lectures where I wrote slides online, and I don't have time to do that now to write it online. So I will take these slides, but still you have some notes in the lecture notes, which also gives you more text around this. So I hope you find this okay. Not perfect written here, but I hope you can read it at least. So we got a question here. Is it possible to implement these automata? And I will show you one way to do that very quickly here. So I call that a controller implementation of these automata. And we do that simply by using memory functions, because you could say that all these states in an automata, they need to be represented as a memory function, because you can stay in a specific state, and if nothing more happened in any output or input events, you will stay in this state, and that's something you need to memorize in every update. So we assume here that you have a function which is continuously updated. It could be, say, for these PLCs, it could be that you update them every 10 milliseconds or something like that, or 0.1 second. So maybe you have seen these set reset latches in digital circuits, and we can use those type of implementations and those type of circuits to implement it. So it can actually both be implemented by electronics and electronic circuits, but also, of course, by software. And in these PLCs, they quite often use these digital circuit analog in the description of that as you will say later. Now I take a more equation way of describing this. And for this set dominant SR set reset latch function, the equation is that the next output is the current input Y if it's high. That is the set dominant. So if YS is high, it doesn't matter what YR is. But if YS is low, if it's false, then you keep the current value, meaning that if U is high, it will keep that value until YR goes high. And that means that this YR negation gets low, and then this will be false. And if also YS is false, the next value of U will be false or 0. So as long as YS is true, U is high, and then when YR, the reset, gets high, U will go low. So this type of circuits can be used to implement these type of equations, and then we will see how this type of equation fits into our automata. So here we have an automaton with 3 states, Q1, Q2, and Q3, and we also represent them by 3 Boolean variables, x1, x2, and x3, which can then be 0 or 1. So the update of the first state variable x1 is when you get an init signal, it goes high. And then you stay high with x1 high until the y1 goes high. And then that is a reset signal, which means that x1 will get low. At the same time, it's a set signal for the next state, because you go then to the next state, x2. But that means that you are currently in x1 and y1 goes high. Then x2 will next time gets high, and you will stay there until y2 gets high, and then x2 gets low. And finally, x3 gets high when you are in x2 and y2 gets high, and then you will stay there forever. So this is a way to implement automata by Boolean equations. And these Boolean equations are perfectly implemented in, for instance, these programmable logical controllers, but also in any other language, including MATLAB, C++, Java, etc. So here is the little bit more complex version of this cylinder application, where I have two cylinders, A and B. First, A, the piston rod goes up, and then B is a pusher that push away the element. And we have actually implemented this for moving around small steel balls. And without going into all the details here, I would say that the behavior here is that first A goes up, then B goes to the one position and then back, and then finally A goes down. And that is what you see here with A going up and down, and in between B is going up and down. And if you look at an automaton for this, it looks like this. An event-oriented, and if you reduce that to introduce Boolean variables for the control signals in the different states, you get this down to 4 states, and then it's only the signals from the plant that are used for the events, and the control signals are then outputs from these states. And without explaining all the details here, because you can see the same type of pattern as I described up here with these equations. You can look at this further and see that in this way you can implement these 4 states in the automaton, and also that the control signals are then state dependent. So this is just a quick way of showing that, well, without going into all details here too deeply, it's possible to implement these automata in biological equations, and then also by industrial PLC controllers. And here is another way to do this with these graphical descriptions. Actually, PLC can be implemented exactly by this graphical models instead of these equations. So now my question is, should I go on, or I mean, time is 12:15 for me, and for you, I think we have passed the time for a break, and then we could continue later in the afternoon, and then I start with the discrete math. Is that okay?
Well, so participants, if you have any questions, you can ask now, or then we can meet in the tutorial session. So it's 4:44 here, Professor.
Yeah.
We will be, like as per the schedule, we will be meeting at 6:30 p.m. India time.
6:30 for you, and
so
earlier for me.
Okay. Fine.
So thank you very much for attending so far, and then we will see each other later in the evening for you.
Sure. So if there are no questions, then we can request all the participants to please put on your videos. We will take a screenshot. I request Samir to do so, because I do not know how to take it.
Yes, ma'am, I'll do it, ma'am. Yes, ma'am, sure.
Is there any method, or you only take print screen?
Yeah, I only take print screen, ma'am. So I've installed Dropbox, ma'am. So it automatically takes that snapshot to the folder. So no need to open the paint. Yes, ma'am.
So participants, it's requested, please put on your videos. We'll be glad to see you also, because virtually it's so difficult for a speaker to speak without watching the faces. Many of you must be teachers, so you must be knowing how difficult it is. And we have spent this difficult time for 2 years.
Yeah.
So my request to Paraj, Neeraj, Sanjay, Nishant, Sarvara Guru, Dipojwal, Arup, Maksud, Siami, Virendra Kumarji. I request you, Rashmi, Atif. My request to you is to please put on your videos. We take a small scene screenshot and then we'll. Hirak, your surname is difficult for me. Basumatari, if I'm correctly pronouncing you. Ma'am, your name is not visible, ma'am. Can you please rename yourself so that we know who you are? Hello. May I request all of you to Sindhuji, Siamiji, Atif, let's be quick. Let's take a quick, Sanjayji, you are not here, perhaps? Shubhangi? So welcome you all to this session. We had a wonderful session. I learned something from controls and signals. So it was something familiar because he connected it with these different states, how to convert from, how to see the whole picture in terms of these states. So on behalf of all of you and on behalf of IIIT-DM Jabalpur, we sincerely thank Professor Bengt for his first lecture. And it was such a wonderful session, sir. We look forward to your second tutorial session at 6:30 p.m. India time. Thank you, Professor.
Thank you. Thank you very much. See you then.
So I'm closing.